Hello everyone, my name is Oliver Hahn and I'm going to present our paper, Semantic Self-adaptation, Enhancing Generalization with a Single Sample. This is a joint work with Sherwin Bahmani, Eduard Zamfir, Nikita Araslanov, Daniel Cremers and Stefan Roth. In this work, we consider semantic segmentation, the task of predicting a distinct semantic class for every pixel in an image. This dense prediction task is particularly challenging in the setting of out-of-domain generalization. Hereby, the training is typically performed on an inexpensive synthetic data, whereas real-world data is observed at inference time. Previous studies rely on the assumption of a non-adaptive model, meaning once the training process is complete, model parameters remain fixed at test time. We challenge this premise, inspired by the idea of adaptive grasping, where a robotic gripper uses an observation input to adapt its technique to the object being grasped. Similarly, our self-adaptive approach for semantic segmentation adjusts the inference process to each input sample of the test data, without sharing any knowledge across the test samples. We chose WildDash as our validation set, which bears closer visual resemblance to the target domains, while still having a distinct distribution from the test domains. We train a model on the synthetic datasets GTA and Cynthia, and evaluate on 4 different test domains, namely cityscapes, BDD, IDD, and mapillary. Based on the original test image, we create a mini-batch of augmented samples by using multiple scales, horizontal flipping, and grayscaling. We pass this augmented mini-batch through a model pre-trained only on synthetic data. Using inverse similarity transforms, we project the obtained semantic maps back to the original image plane. This leads to having multiple predictions for each pixel. Next, we compute the mean of the softmax probabilities along the batch dimension, and introduce a class-dependent threshold. This allows us to extract the dominant class for each respective pixel, ignoring low-confidence predictions. The generated pseudo-label is used to fine-tune the model for a fixed number of iterations. After this self-adaptation process, we compute the final prediction for the test sample using the updated model. To remain within the domain generalization paradigm, we discard the model changes after every test sample. When analyzing batch normalization layers, running statistics from the synthetic source data differ substantially from test domain statistics. To mitigate the covariate shift problem, we introduce a self-adaptive normalization, which improves the test time behavior of batch normalization layers. We compute a weighted sum of mean and variance accumulated during training from the source domain and statistics extracted from the single test sample. Our self-adaptive normalization, or SAN for short, does not only lead to better out-of-domain accuracy in terms of mean IOU, but also to better model calibration, measured by the expected calibration error, abbreviated as ECE, reported in this table. Despite having a stricter evaluation practice and a simpler model architecture than most published work, self-adaptation overwhelmingly exceeds the segmentation accuracy of very recent work. On average, self-adaptation surpasses its ResNet 50 baseline by 12.7% IAU and improves the previous best method by 1.03% IAU on average. Modifying the inference process inherently changes its runtime. We profile the runtime of the baseline model and our proposed self-adaptation. We further compare our approach to the test time augmentation, short TTA, as well as model ensembles. For a fair comparison, TTA and model ensembles use our proposed self-adaptive normalization scheme. Furthermore, we also investigate ensembles in combination with TTA. We observe an expected increase in runtime using our self-adaptation due to the additional model updates, but self-adaptation naturally offers a trade-off between increased runtime and achievable accuracy. Nevertheless, our self-adaptation proves to be not only more efficient than the model ensembles, but even more accurate. In the following, we visualize the performance gain of self-adaptation on a video sequence taken from the Cityscapes dataset. We observe a clearly perceivable improvement over the baseline, especially in terms of image boundary consistency. Our approach exhibits more homogeneous semantic masks with visibly fewer artifacts than the baseline. To summarize, we find that self-adaptation improves out-of-domain generalization accuracy of state-of-the-art methods. We further obtain an efficient accuracy and uncertainty boost by using our self-adaptive normalization. We show a robust and strong accuracy improvement agnostic to training pipeline and model architecture. While we still suffer from increased runtime, we offer a cost-effective runtime accuracy trade-off. We hope that these encouraging results will motivate our research community to study self-adaptive techniques in other application domains and increase the efficiency towards real-time. The code and pre-trained models are publicly available, and we hope you find them useful in your work. Thank you for watching.